trouble. I wouldn't bite that bee if I were you. Okay, hello. Welcome to Lecture 8 on my lectures on Power Series. If you're just tuning in, let me just point out that these lectures are made for my Calc 2 students, and I really assume that you've been sitting in on my Calc 2 class this whole time. It does not fill in background material that you may not have had. So if you don't understand it, don't kick yourself too hard. If you haven't had Calc 2 before, you're not taking it right now, it might be sort of hard to follow. Eventually, maybe I'll link to things you might be able to get to fill in with the background. But until then, it's going to be hard. But if you have had some Calc 2 or you want to try it, this is a lecture from section 11.9 from the book we're using, which is Stewart Calculus. And in this lecture, we're writing functions as power series. And this brings us to last recording I made. We started writing functions of power series, and we worked with functions that were inherently geometric series, 1 over 1 minus r. And now we're going to expand on that, but we're really bringing in one of the most important theorems of this chapter, which is that if you have a power series, it can be differentiated and integrated term by term. And the resulting series will have the same radius of convergence. So what does that mean? Well, if I have this power series equal to some function f of x over some interval, right, with some radius, over some radius of convergence, then the derivative of that function is going to be obviously the derivative of the power series. But the big deal is the derivative of the power series is the series of the derivative. And remember, I'm differentiating with respect to x. So a sub n is constant with respect to x. So when I differentiate this, it's simply like differentiating. Let me pause until dogs are done barking. Okay, dogs seem to be done barking, so let's go back here. So what is the derivative of each of these terms? Well, a sub n is just a constant, right? So we're taking the sum n equals 0 to infinity. A sub n is constant. Well, that means that the derivative of each is going to be a sub n times, now x minus a to the n. Well, a is constant, so that's like x minus 2 to the fourth. A and n are constant. What's the derivative of that? That's going to be n times x minus a to the n minus 1. N times x minus a to the n minus 1. Now notice when n equals 0, that zeroes out. So this is actually rewritten as the sum n equals 1 to infinity of that. A n times n, x minus a to the n minus 1. But the big deal is that you can differentiate it term by term, and since it's a big polynomial, it's pretty easy to differentiate. And again, you can integrate it term by term. Of course, when you integrate, you get a constant. That constant is going to be something that you have to figure out according to the function. But other than that, the integral of f to the x is the antiderivative of f to the x is going to be what I get if I take the antiderivative of each term, which is, well, how do I, oops, sorry, see, let me erase that. Which is going to be c plus. Okay, well, what is the antiderivative here? Well, a n is just a constant. X minus a to the n, well, you could do a u substitution if you want. U equal x minus a, but du is just dx. You should be able to figure out that that's just going to be x minus a to the n plus 1 over n plus 1. In other words, I integrate and differentiate and get another power series. And that's a big deal. And not only do I get another power series, that other power series has the same radius of convergence. It may not have the same convergence at the endpoint of the interval of convergence, but it has the same radius of convergence. So let's do some example using these theorems. So unfortunately for space, I'm going to erase this theorem so remember it, bring it to heart, and we'll do some examples using it. Okay, so here's a couple examples where we're going to try to actually use the theorem we just did, which is that you can integrate or differentiate a power series term by term. So we're still in the process of trying to figure out the power series expansion of certain functions around 0. Later we'll do it around other points, but right now we're looking for the power series expansion around 0. So last recording, of course, we did some examples where we recognized that the power series expansion of something around the power series expansion of something that looked like a geometric series. So now we're going to look at things that aren't really geometric series but are related to geometric series either by integrating or differentiating. So here's a couple of examples here. This first one. Okay, now the key here is to recognize when something is the derivative or the integral of something that looks like a geometric series. And in this case, or something whose power series expansion I know. In this case, what I want you to verify for yourself is that this particular function is the derivative of 1 over 1 minus x, right? So that's 1 minus x to the minus 1. The derivative of that would be minus 1 minus x to the minus 2 times minus 1, right? The derivative of 1 minus x, and that's exactly what that is. Now this one, as long as the absolute value of x is less than 1, radius of convergence is 1, this is the derivative. This is the series n equals 0 to infinity of x to the n. And now the whole point is I can differentiate this term by term. So when I take the derivative of this series, that's going to be the series of the derivatives of each of these terms, which is n x to the n minus 1. Of course, that first term is just 0, so that's the sum n equals 1 to infinity of n x to the n minus 1. And we can change that to 0 to infinity by changing indices, but we don't have to right now. So the idea is this particular function has this power series expansion. That's not quite a geometric series. That's a little bit different, but it's a derivative of a geometric series. And not only that, the radius of convergence is the same. So the radius of convergence in this case, remember, we're expanding around 0, so the radius of convergence is 1. The interval of convergence may not be the same, so we have to check what's happening at 1 and negative 1. So let's do it really quickly. At x equals 1, I'm looking at the sum n equals 1 to infinity of n times 1 to the n minus 1, which is this 1, and that diverges, right? And at x equals minus 1, I'm looking at the sum n equals 1 to infinity of n times minus 1 to the n minus 1, which again, that's an alternating series, but the terms don't go to 0, so that also diverges. So the interval of convergence is negative 1 to 1. So this happens to have the same interval. So this here is the power series expansion of this function here around a equals 0 over this interval. And that's true over this interval. So let's now go to this other one. Now the thing is, this other one I'm doing in terms of this. What's the derivative of 1? What's the derivative of 1 over 1 minus x to the negative 2? Let's just look at that. Let's look at that over the side. d dx of 1 over 1 minus x to the 2. Well, that's 1 minus x to the negative 2, which is negative 2, 1 minus x to the negative 3 times negative 1, right? Which is 2 over 1 minus x cubed, which is almost what we have here. I want you to recognize this as the derivative of that. That's why I do this example. But that's going to be the 1/2 times the derivative of this. The idea is that's 1/2 times the derivative of this. And this I just figured out the power series expansion for, right? As long as x is in this interval, this power series expansion is going to be sum n equals 1 to infinity of n, sorry, d dx of this, of the sum n x to the n minus 1. And that's going to be, that's d dx, that's going to be 1/2 times the derivative of each of the terms, which is n times n minus 1, x to the n minus 2. And again, the n equals 1 term vanishes, so we get, and I'm going to distribute the 1/2 through, I get the sum, n equals 1 to infinity, n equals 2 to infinity of n times n minus 1 over 2 x to the n minus 2. So, recognizing when there's a cubic in the denominator, when the denominator is cubed, it's a derivative of something whose denominator is squared. That's what you're recognizing. When the denominator is squared, it's the derivative of something whose denominator is just straightforward. When the denominator is to the fourth, guess what? It's the derivative of something whose denominator is cubed. And I'm going to actually do something different here. I'm going to do a different example here, just to point out. Let's look at now 1 over 1 plus 1 plus 2x squared cubed. Now this is a lot harder to recognize as the derivative of something, but if you recognize this as related to this one we just did, we can think of this x is equal to minus, go away, that x is equal to minus 2x squared, right? So I'm replacing that x with minus 2x squared. That's going to be the same as what I just got here. This is going to be the sum, n equals 2 to infinity of n times n minus 1 over 2 x, and our x now is minus 2x squared to the n minus 2, and this is as long as 2x squared is in our interval, right? 2x squared is in this interval. Now let's simplify this a little bit. So this is going to be sum n equals 2 to infinity of n times n plus 1 over 2 times minus 1 to the n minus 2 times 2 to the n minus 2 times x to the 2n minus 4. That simplifies a little bit more, but this is written in terms of a power series. And this is, well, when is 2x squared in that interval? That's going to be if negative 1/2 is less than x squared less than 1/2, which is the same as negative 1 over square root of 2 less than x less than 1 over square root of 2. And this is a power series expansion for this thing. Oops, sorry. This is a power series expansion for this particular thing, as long as x is between these two endpoints. So the idea is once you get something like this, you can expand on it. So let's do well, actually, I'm going to do a couple more examples in another video.